we might not see visual equal potential if you're, for example, if you're blind, then there will be no visual equal potential. So this is an objective way to measure infant's visual acuity. So since if infant cannot speak, so in order to make sure that the infant has a well-functioning visual system, we can perform this experiment to measure the infant's visual potential to make sure that we can see something. So also we can use this to check if you lose your vision. For example, when we are aged, our vision might decay due to our health condition, and we can use this to measure our vision condition. So this is a typical visual equal potential. So again, in this waveform, it ignores the baseline. So starting from 0 here, you can see N75, P100, and N135. So this is a typical visual equal potential for human. So this is different for other animals. So this is highly related to not just the visual system, but also it kind of reflects the nervous system and the brain and the visual system in your brain. 好，所以就是这个视觉上的这个诱发定位，它就是当你只要看到一个明确的一个视觉刺激呈现的时候，就你看到一个东西出现的时候，出现这个很重要，就是它要从没有出现到出现，那它就会产生这样子的视觉诱发定位 ，visual equal potential 就是 VEP。那它可以用来确认说你的视觉系统正常运作。那另外呢，就是如果你的视觉系统没有正常运作，那它就会看不正常的记忆。所以它可以用来看说婴儿是不是有正常视觉。那另外也可以看说，如果我们老化的话，我们视觉衰退，那它也会造成 VEP 的改变。所以这边就是一个客观的方式去确认我们的视觉系统。那我们一般人类的 VEP 会长这样子。你可以看到说，从0开始，它在这个大约70毫秒的时候有这样子的 N， 然后在正的时候有一个 P， 有一个 N 这样。So the N75 refers to a negative peak at around 75 milliseconds, and a positive peak around 100 milliseconds. This is called P100, and N135 refers to another negative peak at around 135 milliseconds. So this is how we name the components in ERP. So here the components of ERP refers to a negative or positive peak on the ERP waveform. So it's like the different part of this curve. So this is called the component of ERP. So through this task, we'll use many, so we will have many different times to call something components that they might have different definition. So here I will specify that this is the component of ERP, and it's not the same as the component of other things. 好，所以就是这个我们命名这些 ERP component、ERP 成分，用的就是这个看它是负的 P 或是正的 P， 然后它是对应到说哪一个时间点。那这个单位通常就是 millisecond， 所以75 millisecond 有一个负的 P， 100 millisecond 有正的 P， 然后130这边有一个负的 P。好，那这个 component 在我们这个课里面会一直出现，但是会用来指不同的东西。那所以关于这个 ERP 的 component， 它只是说就是这个波形上 GRP to different component. They use this to discuss how nervous system functions. So they have theory to discuss like what brain is working at this section and what brain is working in this section. So there are each component might relate to a lot of things and a lot of brain functions, and that may relate to some cognitive response. So that's very complicated. So if you're interested, you can search on the literature, and you will see a lot of association of each component with other things. So it's too complicated, so I'm not going to talk into detail about each component here. What we're interested in is how we can leverage this kind of response to build an ECI. So next I'll talk about steady state visual potential. So to evoke this kind of steady state visual potential, we name it SSVEP. We need to use repeatedly visual stimuli. So here it's rapidly repeated. So it has to be repeated like less than 1 second between them. So, for example, if you use an LED light bulb to induce SSVEP, you need to code the brightness of your LED bulb like this, and this can be controlled by a trigger like this. Then your EEG will respond like this. So if you look at the VEP here, every time a visual stimulus presents, your brain oscillates like this. So what if you continuously see the flashing of this visual stimuli? Then your EEG will kind of oscillate synchronized to your visual stimuli. So that will create a waveform, an oscillation that has the same frequency as your visual presentation. So here, this example, you can see within 500 milliseconds, you have 5 repeat lights up of the LED. Then that will create a 5-piece of your EEG waveform within this 500 milliseconds. So this will create a 10 Hz oscillation because you have 10 Hz triggering of your LED presentation. So the SSVEP is this kind of waveform that has the same frequency to your visual stimuli. So if you tune the frequency of your flashing LED, then you will see the SSVEP being tuned by your stimulus frequency. So it can be 10 Hz, it can be 20 Hz, it can be 30 Hz. So quick question, so why we can see a large waveform on 10 Hz, but smaller waveform on 20 and 30 Hz? Anyone want to make a guess?
因为那个20跟30的话，它刺激太频繁，然后脑袋可能不会反应那么大。
对，yeah, could be when you see a flashing at 10 Hz or 30 Hz, your brain response cannot capture the presentation precisely or as quickly as they repeat. So it cannot create a strong waveform that is locked to this frequency. So in some literature, they have this theory. So they can see for different people the strength of SSDP. So that is it's like the power amplitude of the SSDP as the distribution across frequency. So this subject might have strong 10 Hz, but this subject might have strong 12 Hz. And on other frequency, there are different kind of distribution. So I think that's part of the factor that influence this SSDP response. 好，就是说那个有一个可能是说，当你这个闪烁的频率可能比较高的时候，那这个大脑它对这样子的刺激跟反应就没有那么明显，可能是因为说你的大脑跟不上这样子的这个闪烁，那所以它出来的那个 response 比较小。这个在文献上会看到，所以你会看到说，可能这个人他的大脑比较偏好某个频率的刺激，他的反应会特别强。那不同人的话，他强的频率会不一样。So I think, yeah, this is part of the factor that's shown in the literature that your brain might have a preferred frequency band to respond to SSDP. So is there any other factor that might influence the amplitude we observe?
Sensor quality, and also influence.
Sensor quality.
Yeah, the closer to the hair or to the skin or scalp.
So the quality might have some might depend to the frequency of the signal. Yeah. Yeah, I think that could be another factor because your sensors might respond better on low frequency, or might respond weaker on high frequency. And there's another factor that's in play with this is the conductance of our EEG signal, because it's kind of sourced from the local field potential in our brain. And when we measure it from out of the scalp, it has to pass through the conductance through different tissues in our body. So that causes the decay of high frequency signals, because the low frequency signal can pass through these body tissues with better response. So yeah, so another factor would be caused by the measuring of the signal, and that maybe contribute to the nature of the local field potential and the frequency response of the conducting material in the tissues when your electropotential pass through these parts. It has different conductance, different frequency. So that might cause this difference. So usually when we see the power spectrum of EEG, we can expect a higher power at low frequency band and smaller power at high frequency band. Okay, so what if we tune the frequency from 1 to 100 to observe the SSBP? So in 2001, a German scientist, Hermann, reported this experimental result that's a very comprehensive result of SSBP experiment. So this is the stimulus frequency from 1 to 100. This is the response frequency. So this is actually the power spectrum of the EEG during each stimulus, and plotted by the color here. So the dark color means there is stronger spectral response on the power spectrum. So here you can see when this curve is it's called the fundamental response. So you can see on this curve, the response frequency is the same as the stimulus frequency. So this is what we already know, that you can see oscillating waveform that's corresponding to your stimulus frequency. And here we see some other response. For example, here you can see the power line. So this is a country with 50 Hz AC power system. So you can see the 50 Hz spectral response here. And here there are different harmonics. Okay. First, we look at the 10 Hz first. So regardless the stimulus frequency, we always easy to see the 10 Hz response in our brain, because a lot of time our brain has strong 10 Hz, because that's related to either relaxing or fatigue or something. So during experiment, we always see from time to time there is alpha spindle from our suggested EEG. So this is also shown here. And the harmonics, that's because our SPP is not perfect sinusoidal wave. So it has, so it is the composition of the fundamental frequency component with some other harmonics in order to create the special waveform of SSBP. So it contains the first harmonic, second harmonic, third harmonic, and also the subharmonic. So the first harmonic is the double of frequency. So if your stimulus frequency is say 20, then its first harmonic will be at 40. So this is the 40. Peak on the power spectrum is around EEG. And subharmonic is in the half of frequency. So if it's 20, you can see the increase of harmonic. So this is the SSBP response from this result. Any questions so far? And there's something weird that even the author did not add explanation in the behind this. So, and it does not. So so it could be caused by the instrument. That's my guess. There's no clear explanation in this. So this is how we really a very comprehensive result testing. So still this video is a very valuable design SSDP PCI. Questions about? 好，所以 SSDP 就是它被这个总统的伸缩的识别刺激会发出这样的就是12就会看到什么 output 上面可以，然后这个12它就大上，那我们刚刚就问一下同学，那有一个因素是说就是跟你的大脑这个直接有关。那另一个就是你的大脑的讯号从里面去另外一个它本身就有一个那个频带上面插一的那个讯号高电讯号这跟你的这个空间讯号有关，就是电磁电波讯号从这个里面传出来。那应该说这个电位的话，不能从空气形式的传导，然后就是会有频带上的差异。好，然后这个是那个2021年的研究，它对于从1到100的刺激程序，它都做过这个实验，然后他就看说每个一下的power spectrum是什么样子，然后用颜色分析。深色代表这个跑得强的地方，所以我们可以看到 SSDP 它会有一个对应的刺激率跟反应率对应的地方，这叫 fundamental 的反应。那因为 SSDP 的这个脑波波是标准的显波，所以它也对它有好方，所以这边我们可以看到12码，22码。然后这边40分不用好，它这边是22点，它有14，甚至还有30，那10这边是上不上？然后这个33这边，它30这边的镜头，我在这个地方它好像15这个上变现象。这其实是一个证据，就是刚刚跟华说的，就是当你的大脑没有办法对这个快乐闪烁反应过来的时候，对大脑在33无法进行的是合作好，所以就是这些都反映在这个上面。我们可以看到说，它所做的运动上，它的上方面，然后有reverse 在不同的线波。好，然后这边我们可以看到，就是不管在哪个时期。都可以微型前那个10赫兹就是阿尔法的振动，然后这个是跑的50赫兹交流电的跑的，所以它的这个实验几乎很完整呈现这样子的实验，得到什么东西 ？So SSD has been used So SSD has been used extensively. I don't have the video here, but I can look for it later. But besides being used with extensively, it's also used for glaucoma detection because glaucoma refers to the visual loss from your video field. So it's not part of your video field. But if you want to measure which part of the visual video field has been impaired, you need to, so the conventional way is to have a big screen showing different representatives in part of the screen, and the patient has to respond if he or she see the images at different part of the screen. But because it's a big screen, it takes space for this kind of examination. So there are people who is actually my sponsor, he and some partner, they develop VR-based local detection. So you don't need a big screen anymore. Now you have VR goggles. This is such a large display here. And then they use that screen sensors at different parts of the visual field so that they can measure the sensitivity to see if there is a response at a more level. So if the response is weak, then that implies part of the field is lost. 所以这个是一个应用。那 SDE 它可以用来做这个输入字，它可以把做出剪片头参数作为对比成字同频率，然后就看着那个字，然后就量起来是1:1，就可以输入这个字。那另外一个应用是说，它用来测量视觉衰退，就像1:1一样。那它可以用来测量光芒。那像我们做完还要在一个大的模型前面，然后这个病人需要去看说这个荧幕上出现这个信息，他如果看到就没看到，没看到，就没看到，然后就可以测出他前期那个视线已经衰退了。那这个我的白色发现线，就还有公司嘛，这样的。你用原始的主题，然后你用 VR 所以你就需要一个大的潜水放很大的一个，在这个 VR 的装置上面有很大的画面，然后在不同的地方不同的技术，所以我们这样测量这个 SMAT 上，如果在一个它是用不同的去配置，所以它可以让它在某一个频率 SDT 有点弱，或者是1:6。它是1:1块谁是有衰退的，所以这也是一个视力检查的一个。So side video potential that can measure the function. So the auditory this has many components, and this is how it's used to measure the auditory inputs. So this is the headphone. This is the And there are the potential. So this is somatosensory potential. So you measure the tactile response. You receive the tactile. You can see some touches. You can inspect the somatosensory potential. So you can measure not many from the brain. Also very from the nervous system, the nervous fibers, and you can see the rotation of the stomach. You can also measure how fast your nervous system transmits the signal, and that depends on the transmission rate of the axon from what There are also
motor views.
This is not
evoked
potential. This is not evoked by stimulus. This is a potential generated way to execute movement. So when you move your left hand, you will see the response of this. When you move your right hand, you see the response of this. So you can see they are asymmetric. So you see a decrease of amplitude and your right hemisphere around the motor cortex. It's the right motor cortex when you move your left hand, and you see the corresponding amplitude decrease that hemisphere. 所以这个不是一样，是一种 event。它不是以后，它是就是因为你要做动作产生的。它是当你动你的左手的时候，会看到这样子反应出现。那就是左手是对应到这个右边的生活这个。正的下面，如果你动右手的话，左边的正的下面，然后详细的时间上会。And if we look at the motor from frequency domain, see the power decrease corresponding to the motor execution. Here the zero is the subject moves of the hand. So anyone want to guess which hand does thing? So if we remember which vessel is that hand, and where is C3? Yes, C3 is on the left. So the coordinates controls the right part of the body. So this is right hand. That's a good guess. So so this measure is response has measured the motor response in the right hand. Here you can see the ER, that is the power decrease of the alpha, beta, and due to caused by your motor shift. And this is ER, so it's the breakdown of the power after the event-related desynchronization. So here the desynchronization means the power increase, and synchronization power increase. So it's almost the same every time. So what if you don't perform this imagine your mind. You can still see the ER as the power increase. So here this is a way to separate signal. Here reverse to spatial component. So if you look at the left codex, the right codex, we can look at the power response response. Here you can see when subject is moving that hand. We can see at the right that hand here, that I. So that IC refers to the response at projects. The right IC is at right. So when you move the left hand, see the very easy implementation as the power decrease at the right. And when you move the right hand, you can see the easy implementation as power decrease at. So this means that we can create this kind of response using multiple materials. We just have to imagine. So this is a very useful response of CI. So you can simply imagine the right hand. You're actually doing nothing, just sitting there. And doing this kind of imagination and control something, because we can detect the motor potential and recognize if it's left hand or right hand to imagine. So我们用这个动作想象的反应就可以去做这样的ECI。然后可以用来清洁手机。So you can use multiple material to control a robotic arm. You can control it to move like this. It's actually for direction up, down, right, grab, or even forward, backwards. So apparently that hand is not enough. So they might have to add more like foot, motor material, tongue, motor material, add different part of create this.所以像刚刚这样子的机械动物，但是左手右手的话，它的这两拳这样就够了，所以不要再加更多的这个选项，像动脚的更多，那就可以把这个动作的选项增加这样子的动作控制。Question so far? So, E300 is part of the visual first major of the other component. So it usually refers to the positive around 300 the major. So here the P3 comes with the negative P. But if you look at the y-axis, you can see that. So in some of the ERP, they like y-axis. It's just the representation of. So the P300 refers to attention. So if you see something present, you then have to be happy. But if you're paying attention to this, you will have strong E300. So E300 is also useful potential for building PCI. Okay, so this is the power regions anywhere back to 5 milliseconds. Some instantaneous potential followed by action
reaction is actually and
it can be
be
elicited by
elicited by our paradigms,
stimuli brings like high probability
non-part,
and low
low
probability
targets.
So it's like we have two
colors
colors,
of balls,
and one of the colors
presents
high
high
frequency,
frequency,
and the
and
other
goes with the low frequency.
So
So
the one that's
the
high
one that high
probability
probability
is
is normal,
ball,
and
one
the one with low probability
harmful.
So
The
the
P300 is specifically strong speed
optical
stimuli. So it is also applied
to
other type
of
potential. When you
potential.
have
They
a
have
auditory
experience.
you can have a
Have
tone
a
that's
tone that's normal,
another tone that's off tone, and you create
P300
auditory response as well.
process.
So this is
So this is from literature.
They show
the
potential of standard stimuli and optical stimuli. They also calculate
the difference between the two cells.
You can see
You can see the
strong difference between standard
standard
optical
stimuli
is
around
here.
here.
So for different
Between the
individuals,
they
they
see
see the
different
time region of
P3.
So they are also
using
to measure the development. So they recruit subjects from young age, old age. This is difficult because they can people from different ages, such as now, they this is a review and analysis. So they conclude this from literature. And we can see the P300 goes from here when you're young, when you're very little, here when you're a young adult, and then goes later in age. So this is saying that because P300 is responding to when you perceive a stimulation, you have some reaction on it. So this if the P300 presents earlier, that means we have fast response. So that kind of shows that our ability for visual perception is well developed at this stage. Kind of getting decay when we get older. So anyway, P300 can be used to do ECI speller.
First, we'd like to show you a set of processes that is unedited sequence, subject
indicated by control device.
In under 30 seconds, we have established contact and are successfully measuring EEG on all channels. Raw unmeasured signal from 0.5 to 100 hertz is shown, demonstrating how fidelity of our systems made possible by complex combination of sensors, mechanics, and electronics. With the headset in place, we can now start the live streaming layer mapping in a single button. In the open by
They also use the open by product training.
the output from our system is limited to 10. Here, we are configuring the driver to enable automatic triggering. To check the signal quality, go to simple scenario setup to display the raw EEG, filter EEG, plus the time frequency. In addition to those PCIs, we'll provide you with a variety of real-time visual information. On the left-hand side, you see a spectrum of EEG signal.
These are all functions of the control device.
On the bottom right-hand side, you can see the EEG signal after passing into the simple capacitors provided by
There's raw data and filter data, and there's spectrum
as the subject closes your eyes, you can see the alpha burst signal of the EEG spectrum. This sequence demonstrates how quick and effortless it is to set up a system. For the
Here's a view, you can see the paradigm of P300. There's the screen with different letters laying out here, and it's flashing one time, flashing at a row or a column one time, and so it's actually using the time interval between the interval between two P300 to recognize which letter you're looking at.
This will be used to train the filters and classifiers. Here is a replay of the entire training session in high speed. You can see the raw EEG at the bottom half of the screen, as well as the time average response of targets and objects. As enough methods are collected, you can clearly see the P300 devote response shown in green. Likewise, the red traces show the non-targeted responses, which do not have the characteristic. With the training complete, we can now conduct an online experiment. The subject is asked to spell out dry energy.
所以它用这种 flashing， 然后它去看说 P300 侦测到的时候的时间间隔，它就可以知道其他是什么时候。然后我们现在就要输入这个 ERY 的时间。
Primarily to select the correct channel from the LSM data stream. In this demonstration, we have used 12 total repetitions per character. It is likely that higher performance can be achieved with a customized signal and the use of our system's wireless hardware training. However, we want to show you just how easy it is to get started using freely available tools and mobile applications.
好，所以我们这边可以看一下 P300 它的输入的速率，大概就是可能要好几秒钟好一次。So this is the efficiency of P300. You can see it takes a few seconds to input one letter.
Our subject has successfully spelled out dry EEG, completing our demonstration. The software tools shown here are compatible with our entire family of mobile EEG products, ranging from 17 channel
Okay, so this is the concept of P300 speller. So if you want to input the letter H, then you will detect P300 when the row of H and the column of H flashes. So since H is your target, so you can detect P300 when it's flashing on this row, and when it's flashing on this column, since H is non-target, so there will be no strong P300. So it can detect the occurrence of P300. They call it target event, and others that are non-target event. So with this time sequence, then they can detect which letter you're looking at and input the letter on the screen. So the target user of P300 BCS Builder is of course not us, because we have other ways to type more efficiently. So this is for severely disabled people, and especially the ALS people, or locking patients, or brain injured. So these are all severe paralyzed people. They need this kind of interface to communicate. So the advantage of using P300 is that it takes low requirement of fixations. However, the limitation is that the flashing is annoying. And the idling problem is that if the subject don't want to input anything, then the BCI is still detecting the response. Then it's hard to identify if the subject wants to stop this program or not. So this is another thing, since those locking patients, they don't really have a way to express if they want to stop inputting or stop this program. So this takes other ways to detect this kind of intent from the subject. 所以这个 P300 它的好处是说，它可以就是不用一直盯着同一个地方看，那就看着它要输的字，但是它这个闪烁的这个 pattern 还是会让你不太舒服。然后还有就是说，你怎么样知道这个小姐她现在不想要去input任何字？那这个 DCI 在运作的同时，你要怎么知道它是好的？那这个是一个蛮大的问题，尤其是当那个subject真的没有任何方式可以表达的时候，那就会需要一些手段才能知道说他要不要去停止。Okay, so I'll stop here because the TA. Okay. So today we will announce our homework that's about EEG analysis. So our TA Youchen is leaving because he's going back to his hometown. But he has prepared a video tutorial for us to show you how to use the EEG lab, because that will be the major tool for you to do in this homework. And this is so we introduced EEG lab in our previous lecture. It's a graphical user interface based on MATLAB. So you can load the data and analyze the data by clicking the options on the menu. So it's relatively easy for beginners to start analyzing EEG data. And there are also some bonus problems in the homework if you're interested in the kind of the mathematical techniques behind these EEG analysis. You can try to take the challenge and see how you can solve the mathematical problems to get bonus points for your homework. So this homework is individual, so each one in our class has to submit your homework before the deadline.所以就是今天我们会就是公布这个第二次的作业，就我们把大家做完公布第一次，这个是第二次。然后第二次的作业它会主要是分析 EEG data， 然后我们主要用 EEG Lab。那 EEG Lab 它是一个图形界面的软体，是在 MATLAB 上面运作的。然后所以建议大家就是安装起来。那个它的操作呢，就是刚刚柚子他其实有准备一个教学影片，所以大家可以看他的教学影片，然后就知道说那个要怎么用。那因为是图形界面，所以它可以很快让初学者就是你载入你的 data， 然后你去点里面的选项，然后就可以得到一些分析的结果。那就你可以照他的这个 tutorial 去学，然后照着 homework 指示去照着做，就会得到这个分析的结果，然后可以回答你的问题。然后另外有一些额外加分的这个数学推导的题目，那这个是你可以去另外再试试看，那这个是不是必答的问题，就是加分的。So, I think I skipped the break, right? Didn't get the break. So can we take a 5 minutes break? So that we can take a break and come back at 11:40. Okay, let's continue. So, you guys just saw the video is demonstrating the P300 speller. So when a subject is using P300 speller to type, you can see the letter being input one by one. But what if you see a letter that's wrongly detected? So, for example, you want to input with E, but it comes out with F, then in your brain you will detect this kind of error, and it will will create another response that's induced by the error you perceive. So it's called error-related negativity. It's another type of ERP. So you can imagine when we let the subject using P300 speller, we measure the P300 to detect the letters, and we will also measure the error-related negativity when we have a wrongly classified letter. So during that experiment, we will measure P300, and we can also see the error-related negativity. So they are different type of ERP. So this is another P300 paradigm. So you can see it's not for freely input. It is a program session for this subject. The subject has to follow the cue of the cue presented by circling this letter, and then the subject has to input with Z. And another Z here. Okay, so you can see it just wrongly detected the letter. So it was to input with Z, but it comes with a space. So that's when the error-related activity occurs. Let's say it again. It's PIZ. So the first Z is correct, but the second one was not detected. So this is when the error-related activity occurs. So for other typing, the subject did not see the error. It comes with some kind of ERP. It's actually another BEP and probably another P300. But when it goes with error, then you will see a different ERP waveform. And this difference is responding mostly at CZ around the central part of your scalp. So this can be used to check if the subject perceives something's error. So not just for the P300 speller, you might be able to detect, like for example, when we are using a computer within the software interface design is not good, then you might run into some cases that you think is not very good for using, and you might create some error-related negativity in your brain. So that could be an objective way to measure the internal feelings of the user to some kind of user interface. 好，所以刚刚讲这个 P300 speller， 那如果它这个输入都正确，那就 OK。那如果它输入不正确的时候，当它有一个错误的输入的时候，那这个 subject 它会侦测到这个错误，它会产生另一种 ERP 是跟侦测到错误有关。那所以像这个例子的话，它的第二个 Z 并没有侦测成正确。那所以跟前面这个 Z， 比如说前面这个 Z 它看到它知道是正确的，它看到 Z 它就是会产生一个视觉，会产生 BEP， 会产生 P300。但是当这个侦测错的这个空格出现的时候，它会产生一个 error-related negativity， 它就是在它的这个 BEP 上面，它会有多了一个另外的成分。那这个 error-related negativity 呢，它是在那个 CZ 附近有最小的范围。好，所以我们现在可以看到就是这个 你看到的 difference 最强的就在这个 CZ 的地方。那这个东西呢，它一方面可以让我们知道说它在品质的时候，使用这个 VCI 的时候，是不是有遇到错的输错的时候。那这样我们就知道说这个 subject 其实不是要输入这个。那我们如果只知道这个，可以修正。那另一方面，我们可以把它拿来当做说，他平常可能在使用一些东西的时候，他如果遇到这个设计的不好的地方，那他可能就会一直觉得有错误。那这个可能也可以变成是一个使用者对某一个使用界面或者操作方式上，他觉得有不好的地方的一个客观的显示方式。Okay, so when we detect this error-related activity in a PSAS builder, then we will know that the subject actually doesn't want to input that letter. Then we can have a chance to make some correction. Maybe we can change the letter to the second likely option, or there might be some other way to make a certain correction to make the efficiency better. So in summary, the ERP signals are time-lock pattern, and it uses the averaging across different trials to enhance the signal. But that's only for those responses synchronized to the event onset, and it will eliminate the irrelevant frame response. And next time we'll talk about spatial filter. That's another way to extract signals. And so we will see how those component analysis how they perform spatial filtering to the EEG. And so for time-lock pattern, we can use ERP, but for spontaneous pattern, we need something else. So we will go through some of the approach. So in summary, the feature extraction of EEG is like to enhance the signal we observe from the brain. And to understand brain is pretty much like trying to understand a language that no one knows how to use. It's like an alien language that you want to decode this alien language. So it's like when scientists want to decode the ancient Egyptian letters. So they need different approach to extract information from the data. So here our EEG comes with the temporal waveforms, so we can use, and we design an experiment with specific stimuli to try to induce the response again and again, so that we can average across the trials to enhance the signal. And another way is to put more sensors, because the signal is weak. Then we can put more sensors on the scalp to enhance the information we can measure. So in order to process the signals measured from multiple sensors, we need to have spatial filtering, because that refers to, we call it spatial because the lectures are in different positions on the scalp. So we're using the information across the sensors at different spaces. So next time we will go through more approaches to extract the signal from EEG. 好，那个今天讲的这些呢，就是整理了就是关于 ERP 这个东西的一些介绍。那 ERP 这个东西，它是用来去增强这个时间同步的这些大脑反应，所以它靠着这个不断的给予同样的刺激，然后给这个大脑去看它的反应，然后去利用这个反应跟 跟事件有没有相关的特性，来去将事件相关的 brain response 增强，然后没有相关的 brain response 把它压下去。好，那就是我们这种手段呢，就像是去观察一个，应该说像去读懂一个没有人懂的语言。好，就像是我们大脑它的运作的这些 pattern 就是没有人懂。那我们要怎么样去把它的一些里面的意思找出来？那所以我们利用 ERP， 我们可以取得一个方式，就是至少说我们知道跟这个刺激相关的东西，然后一直重复给它弄下去，它可以重复出现，我们经过平均把它增强，然后去确认出来说某一种 response 是跟随着这个事件所发生的。那另外就是因为这个讯号很微弱，所以我们可能就需要用更多的 sensor 来增加讯号的强度。那所以我们布置不同的电极在我们的头上，那目的就是说可以增强我们两道的资讯。那要整合这些不同通道的这些讯号呢，我们就要靠一些 spatial filtering 的方式。那会叫 spatial filtering 是因为这些通道它们在头的不同地方，所以我们对于这个讯号之间的整合是一个空间纬度上面的处理，所以叫 spatial filtering。那所以下一次的课我们就会去讲这些更多的 approach， 那包括就是如果不是太大的 pattern， 那我们有没有什么方式去增强这个讯号？我们可能会有一些这个频带，利用一些频带能量的一些分析啊，或者是说我们想办法去除这个时间上的不确定性啊，或者说我们就用设计一些 spatial filtering 方法，那通常都是怎么样去整合不同通道的讯号，那它就会用到一些成分分析，这种 component analysis， 那像是组成的分析、独立成的分析，然后包括像这个后面这边有放的什么 CCA、GRC 这些都下一次会介绍，然后用不同的方式去将我们要的讯号做一个适当的增强，然后另外也是设法压低不是讯号的成分。那这个就仰赖我们设计实验上的一些方式，或者说我们对大脑的一些基本的了解，可以设计一些这些手段去达到这样的效果。Okay, any questions so far? Okay, so is there any volunteer who wants to summarize this lecture in 1 minute? Okay, this is also for bonus point. It's a good chance. Just 1 minute, so it's quick. You don't have to repeat what I said, but it's most about repeat what you hear in 1 minute. Anyone?